Let's talk about the many derivatives of a function of two variables. This will work for 3 or more variables as well, but that's not what we're focused on right now. Let's suppose that we have the domain of a function f of xy. And if we pick some random point like AB, we already know how to find two of the derivatives. We can find the slope of the function in this direction by finding fx and evaluating it at AB. We can do the same thing in this direction by taking fy and evaluating it at AB. But we know two more. If we know the slope in this direction x, we also know the opposite slope is in the opposite direction. So we just fill that in. Minus fx at AB. Ditto downward, where we would have fy at AB, but we put a minus sign on it. Now comes the big question. How do we find all of the other derivatives in all of the other directions? Well, pick a direction. Let's just pick theta, where it's measured in the usual counterclockwise way with respect to the x direction. Sure, it would be nice to find the slope in this direction. It's called the directional derivative. And this function, which I haven't drawn, it's a three-dimensional graph, but we're just looking at the xy plane. We can say the directional derivative in the direction u, where u is this unit vector, okay, probably not to scale, evaluated at AB is equal to this amazing little combination. You take fx, evaluate it at AB, multiply it by the cosine of theta, add fy, evaluate it at AB, multiplied by the sine of theta. Check it out. If you plug in 0, that's just pointing you in the same direction as x. This is 1. This is 0. And you get fx at AB. If you plug in pi over 2, you're going to get fy back, evaluated at AB. And in all other directions, you get a combination of these two components, your fx and your fy. And that's infinitely many derivatives. But check out how you can rewrite this. We often break it up into vector notation. So here's the fx and fy, and here's a dot product with cosine theta, sine theta. Oops. I hope you recognize this. That's the typical unit vector for any given direction. If you dot these two, you get the directional derivative. There's a lot of stuff going on here. This fellow right here has a special name called the gradient function, evaluated at AB. And of course this guy, he's just our unit vector u. Now you know a few things about unit vectors. You don't have to write these in angle form with trigonometric notation. I mean, you know some of our favorites. Here's one. 1/2 root 3 over 2. Okay? If this was your unit vector, you'd be looking at 60 degrees. Right? About this? Okay? If instead you were looking at some popular result like, I don't know, we've seen this guy before. Those don't look like trigonometric functions. But we already know that's a unit vector. And it's about what? 53.13 degrees. Okay? So now that we've done this part, we've learned how to find a directional derivative. We've learned what the gradient vector is. I'll label that. And of course your arbitrary directional constant. Just make sure it's a unit vector. You don't have to worry about angles in that case. How do you use this? Well, for example, suppose you pick an actual function. So here's a function I want to use. F of xy equals x squared plus xy plus 3y squared. If you draw contour lines for this guy, you're going to find out that you get a bunch of elliptical contour lines. In fact, here's an illustration. In particular, suppose you decide to look at the point 2, 1. So you're going to get 4 plus 2 plus 3 equals 9. So on the contour graph, here's 2, here's 1, here's the point we're looking at. All of these points on this ellipse have the same function value 9. Now what do we do? Let's find the directional derivative there. Because we've learned how to do that, let's find the gradient first. This is sometimes called del or grad. And the first slot will have the partial with respect to x. The second slot will have the partial with respect to y. So let's see. 2x plus y. And then x plus 6y. If I evaluate this at our point of interest, see what we're going to get. 4 plus 1 looks like a 5. And let's see, 2 plus 6, we've got us an 8. All right. I'm going to sketch this on the graph, and I'm immediately going to run into a problem. I don't have enough room. If you take a look at this, this is 1 unit, okay? And what do I need? 5 and 8. So I need to go over 5, and I need to go up 8. Well, I can't do that. But I can scale it down a bit and get a fairly decent reproduction. Over 5 units, 8 units, it's scaled down. If you look at the scale on this guy, this is 2. So 8 would be off the top. But I did do it proportionally. And I want you to notice something. There's a right angle here. The gradient vector is perpendicular to the contour line, to the level curve. Now think about what this means. If you were walking on the level curve, your rate of change would be 0. If you want to maximize your rate of change, you have to step off that level curve. You have to step off in a big way. So when you do that, your best way is to walk right-angled off the contour line. So in other words, the gradient vector points in the direction of greatest change. Let's find out a little more. When you're looking at this gradient vector and you know what you need to do, if I were to pick a unit vector function, like the one I had a little while ago, 3/5, 4/5, let's find the directional derivative. Well, this is pretty easy. 5,8 dotted with 3/5, 4/5. So what's going to happen? Well, I'm going to get 15/5. Okay, and then I'm going to get 32/5. And if my arithmetic is right, I think I've got 47/5. Now we also know if we just looked in the x direction, the rate of change is 5. If we just looked in the y direction, the rate of change is 8. But in this direction, it's what? 9.4. Okay? Now the other thing is that this magnitude, remember what we're doing. Here's 5/8. We're multiplying it by a unit vector, whatever that unit is. How big can you make this? Only if these are parallel, because then the cosine of the angle between them is 0. Excuse me, it's 1. The angle is 0. The cosine is 1. And this product, this dot product, is maximized. Fun facts. 1. The magnitude of the gradient is the maximum possible directional derivative. Second fun fact, the gradient vector points in the direction of maximum change. Those important facts about the gradient vector could serve you well. And that's it for this one. Mm-hmm.